Hello, today we're going to focus on 2.2 forces. Forces are push or pull measured in newtons. One force we are very familiar with is force of gravity or weight. The very concept of push and pull imply direction, therefore forces are vector quantity. The direction of the weight is down towards the center of Earth. If you have a weight of 90 newtons or 90 N, your weight can be expressed as a vector quantity 90 Newton downward. The formula is W equals to mg, and g is acceleration due to gravity. Calculate the weight of 25 kilogram object. Solution: mass is 25 kilogram, g is 9.81 meter per second. W equals to mg, which is 245 Newton. We sketch a mass as point particle, a dot, and the weight as a vector in a free body diagram. Mass, force downward, which is weight. This is free body diagram. For example, when you set a mass on a tabletop, even though it stops moving, it still has a weight. Note that the weight and the normal force are same length, they balanced, or they are in equilibrium. The normal force is called the surface contact force, sometimes called reaction force. Tension T can only be a pull and never a push. Friction tries to oppose the motion here. Friction is parallel to the contact surface, and normal is perpendicular to the contact surface. Friction and normals are mutually perpendicular. Friction and normal are surface contact forces. Weight W is an action at a distance force. Weight is sketched from the center of an object. Normal is always sketched perpendicular to the contact surface. Friction is sketched parallel to the contact surface, and tension is sketched at whatever angle is given. An object has a tension acting on it at 30 degrees as shown. Sketch in a force and draw a free body diagram. So weight is drawn from the center down. Normal is drawn perpendicular to the surface from the surface. Friction is drawn parallel to the surface. So we're going to draw a free body diagram as a dot. Weight downward, reaction upward, friction opposite to the motion, and T is whatever angle. An object has mass of 25 kilogram, a tension of 50 Newton, and a friction force of 30 Newton are acting on it as shown. What is the resultant force? Since the weight and the normal force are cancelled out in a y direction, we only need to worry about the force in x direction. So W and R are cancelled out. Net force here, the tension is 50 Newton and the friction is 30 Newton. So resultant force is 50 minus 30, which is 20 Newton to the right. An object has exactly two forces, F1 and F2, applied simultaneously on it. What is the resultant force's magnitude? Net force is equals to vector sum of F1 plus F2. So we simply graphically add the two vectors like this. So ending of the first force is beginning of the second force, and that's our resultant force. Magnitude is given by Pythagorean theorem. F net squared equals to 50 squared plus 30 squared, and F net is equals to 58 Newton. What is the resultant force's direction? Direction is measured from the x-axis, so the angle is theta. Opposite and adjacent are given directly, so use tangent. Tan theta equals to opposite over adjacent, 30 Newton over 50 Newton, which is 0.6, and theta equals to 31 degree. An object has exactly two forces applied simultaneously to it. What is the resultant force's magnitude? Begin by resolving F1 into its x and y component. That is x component of F1, which is 50 times cosine 28 degree, 44 Newton. And this is y component of F1. Y is opposite, so 50 times sine 28 degree, which is 28 Newton. F net in x component, we have only 44 Newton. F net in y component, we have two forces, 23 Newton from F1, and F2 is 30 Newton. Total is 53 Newton. So resultant force is equals to F net squared equals to F net x squared plus F net y squared. F net x squared is 44 squared plus F net y squared equals to 53 Newton, and total F net is 69 Newton. Recall that friction acts opposite to the intended direction of motion and parallel to the contact surface. Suppose we begin to pull a crate to the right with a gradually increasing force. We plot the applied force and the direction force as function of time. Green in tension and the red in friction. And when object is not moving, static friction is applied. That is a static friction. When objects start moving, we have a dynamic friction. During the static phase, the static friction force exactly matches the applied force. Static force increases linearly until it reaches a maximum value of F static max. The friction force then almost instantaneously decreases to a constant value, Ft, called dynamic friction force. That's one. Take note of the following general properties of the friction force. Static friction is larger or equal to 0 and smaller and equal to maximum static friction. Dynamic friction always smaller than maximum static friction. And dynamic friction is constant. So what exactly causes friction? People in the manufacturing sector who work with metals know that more you smoothen and polish two metal surface, the more strongly they stick together, brought in contact. In fact, if suitably polished in a vacuum, they will stick so hard that they cannot be separated. We say that the two pieces of metal have been cold welded. At the atomic level, when two surfaces come into contact, small peaks on one surface cold weld with the small peaks on other surface, like that. Applying an initial sideways force, all of the cold weld oppose the motion. If the force is sufficiently large, the cold welds break and new peaks contact each other and cold weld. If the surfaces remain in relative sliding motion, fewer welds have a chance to form, called the coefficient of friction, which depends on a composition of the two surfaces as a ratio of friction force over normal or reaction force. Since there are two types of friction, static and dynamic, every pair of material will have two coefficient of friction, static coefficient of friction and a dynamic coefficient of friction. In addition to the roughness or smoothness of material, the friction force depends, not surprisingly, on a normal force. The harder the two surfaces are squished together, the more cold weld can form. Here are the relationship between a friction force and coefficient of friction, and the normal force, which is on your data booklets. Okay, let's do a question. A piece of wood with a coin on it is raised on one end until the coin just begins to slip. The angle the wood makes with the horizontal is theta 15 degree. What is the coefficient of static friction? So we have the weight downward, we have reaction force, and we have a static friction. Let's write it down. That's the weight, reaction, static friction. Weight has two components, y component and x component. The angle here is theta, and angle here is also theta. So the opposite is gonna be w sine theta, and adjacent gonna be w cosine theta. Resultant force in y component equals to 0. So means resultant force in y component equals to 0, which means r, which is r minus w cosine theta. W cosine theta equals to 0, and that is r minus mg cosine theta equals to 0. The coin just began to slip, so its resultant force in x component equals to 0, which is friction force minus the x component of the weight, which is minus w sine theta equals to 0. That is friction force minus mg sine theta equals to 0. Maximum static friction, which is equals to coefficient of static friction times the reaction force, and from here coefficient of static friction equals to F max divided by R, and the friction force is from here. Friction force is equals to mg sine theta, and R equals to mg cosine theta, and mg's are cancel out. We get sine theta over cosine theta, which equals to tan theta. Tan 15 degree, and that gives us here mu d equals to, we plug in, that gives us 0.268. Therefore, the coefficient of static friction between the metal of the coin and wood of the plank is 0.268, practically tan 15 degree. Now suppose the plank of wood is long enough so that you can lower it to the point that the coin keeps slipping, but no longer accelerates. If this new angle is 12 degree, what is this coefficient of dynamic friction? So we have reaction force upward, we have the weight downward, and we have the friction force. We draw x-axis, which is parallel to the surface, and we also draw y-axis, which is perpendicular to the surface. Weight, this is reaction force, this is a friction, and weight has two components. Opposite is w sine theta, adjacent is W cosine theta. Since the object is sliding parallel to the surface, so net force in y component equals to 0, which means R minus W cosine theta equals to 0, which means R equals to mg cosine theta. And the object is actually sliding but no longer accelerating. Acceleration 0 means it's moving with a constant speed. So resultant force in x component also equals to 0. Resultant force in x component is equals to 0 because object is moving with constant speed. F friction minus W sine theta equals to 0. That equals to dynamic friction equals to mg sine theta. And we know the dynamic friction is equals to dynamic friction coefficient times R. And the question is asking the coefficient of dynamic friction. So coefficient of dynamic friction equals to dynamic friction over R, and dynamic friction mg sine theta, and R is here, which is mg cosine theta. Mg's cancel out. That gives us sine theta over cosine theta, which is tan theta, and the angle is 12 degree. So tan 12 degree gives us 0.213. So therefore, coefficient of dynamic friction between the metal of the coin and the wood of the plank is 0.213. Everybody continue in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by force impressed thereon. So that is, if the velocity is 0 or velocity is constant, then net force equals to 0. If object is moving with a constant speed or at rest, the net force equals to 0. And this is called condition for translational equilibrium. As a memorable demonstration of inertia, matter's tendency to not change its state of motion. Consider this: a water balloon is cut very rapidly with a knife. For the instant, the water remains at rest. So that's the inertia, right? Concept of inertia. Don't try this at home.